Okay, like we saw this key rental problem for which we could do it. And there were also weaker notions that were problem specific. For instance, in the very general setting, it's called the expert setting. We said that we could compete with the best expert in hindsight. Okay, so if you have a bunch of people telling you how to play at every step, then you could compete with the best one in hindsight. Okay, and this is related to things that some of you may have seen in the machine learning class. So it's related to boosting in particular. Actually, did you guys, for those who took the ML class, did you actually see online learning?
Yes.
Oh, okay. So that's exactly the same as this expert one. Okay. So that's one. And then we saw, okay, competitive ratio is when you try to compete with the best answer in hindsight. The other thing we saw last class was this, we started looking at it basically, was this interesting notion of how you do computation with failures. Okay, so suppose some logic gates fail or something like this, then can you still perform meaningful computations? Okay. And we phrased it as a game. Okay, so we phrased it as, so it's called Ulam's liar game. That's he was the mathematician who first proposed this. And you can phrase it as a game by saying, okay, you ask 20 questions, a person A thinks up a number between 1 and 100, person B is supposed to guess it, and A is allowed to lie at most 2 times. Okay, so this is the puzzle way of phrasing it. And so you can generalize this. You can say, you suppose one thinks a number between 1 and n, and you ask questions, and you're allowed to do q lies. Okay. So last time we saw a very clever solution by Spencer and Winkler, and what their main contribution was essentially to convert this thing of this game kind of a thing to a full information game. Okay, so this was their main contribution. So we said that you can view this as a full information board game. Okay, so we had this thing of you have these post-it notes and you push them to the right kind of a game. Okay, so this is what we saw last time. And using that technique, what they could show is that even if you have 1/3 fraction of the answers to be lies, okay, so this sort of thing is relevant when you have noisy computation. With some probability, the computation could just be wrong. Okay. So then, even then, you can actually do this binary search kind of a thing with just log n queries. Okay, so this is what we didn't see a full proof of this, but we saw the main technique. And the other thing we saw last time was this thing where, suppose you ask all questions beforehand. Okay, so suppose B is constrained to ask all questions beforehand. Then we saw that there was this nice equivalence to error correcting codes. Okay, so the questions that we were considering were of the form B gives A a collection of sets, okay, S1 through Sm, and A is supposed to answer if the number that he selected belongs to each of these sets. Okay, so he gives n different true/false answers. Okay, so this was the setting we saw, and the key idea for B to do is he's supposed to form questions so that for any 2 distinct numbers that A picks, the true set of answers actually differ in a lot of bits. Okay. So if A picked I, then he's going to get some set of answers. If A picked J, he's supposed to get some other set of answers. And these 2 sets of answers are supposed to differ in a lot of bits. Okay, so in at least 2q plus 1 bit. Then even if A lies on q of these answers, B can uniquely recover the right answer. Okay, so this was kind of the key thing that we saw last time. So we said that, so this was also, this provided the connection to error correcting codes as well. So what we said is the true answers to these questions for any distinct I not equal to j actually differ in a lot of bits. Okay. And so if you look at the answers for I as a, so the set of answers for I So this is just a vector in 0, 1 through to the end. Okay, so this is just an m-bit string, it's a set of true false values, and this is a true answer. And the answer that A gives will be at a distance q from this, okay, because he's allowed to lie only q times. So if you ensure that the true answer of I and the true answer of J are very far apart, are at least 2q plus 1 apart, then you can never confuse I with J. Okay, so this was the thing that we saw. Right, and and this sort of an object where you have, so if you define this TA of I to be the encoding of I, then the encoding of two different strings differ in a lot of bits. That's what's called an error correcting code. And so this is what we saw last time. Okay, and we also said that you can prove that as long as the number of errors is less than 25%, then you can just ask O of log n question. So again, this is not, we didn't quite prove this formally, but this turns out to be true. Okay. So any questions about this before we move on to yes, so I guess the point that you should keep in mind is this notion of you ask questions where the true answers will actually differ by a lot. Okay. So that way, even if one lies a small percentage of the time, you can still recover what the true answer is. Okay, so that's the main idea. And how you do this efficiently and so on is actually tricky, and we didn't even start doing that. Okay, so some of you are doing projects. All right. So this is what we did last time. And let's now move to a more broader review of stuff we've done in the course, okay, because I think we've covered a fair amount. As Mohsen was just saying, it's hard to believe that this is the lecture number 28. Right? There's been a lot of stuff. Okay. So what all did we do? Right? So let's try to do a quick recap. So we started off with very basic algorithmic paradigms, right? So these were things that many of you probably saw in your undergrad. So these were things like divide and conquer, greedy strategies, and so on. Towards the end, we also saw this tool which really belongs to this basic paradigms. It's this notion of optimization. Okay, so when you see a new problem, you might want to phrase it as an optimization problem and just try to solve it. Okay, so in many areas like learning and so on, this is all they do. Right? So it's all they used to do for a long time. They would just phrase the problem as optimization, give it to an optimization solver. Okay. So this is another powerful way to deal with problems. And of course, these general paradigms of divide and conquer, greedy, and so on are very useful. All right, and we also saw how to analyze algorithms. Okay, so and this, as hopefully all of you are convinced by now, is not always easy. Okay, so sometimes it could be quite tricky to analyze algorithms and reason about correctness. Okay, so and this is normal. Okay, so it is most interesting algorithms have non-trivial analysis. Okay, so it could be sometimes tricky. And we saw, generally speaking, how to reason about the running times and how to reason about correctness and so forth. Okay, so this has been a common trend throughout the course. And then we moved on to this notion of algorithms on graphs, where we saw things like shortest paths and so on, which are also very basic algorithms. And one non-trivial example here is that of flows. Okay. So in flows, we saw this notion of augmenting paths, which is pretty clever. So it's you could make mistakes and then you have a clean way of correcting for them. So this notion of a residual graph plus augmenting paths is very nice. So that said, flows, oh, and we also saw this very nice notion of the max flow min cut theorem. And yeah, it's one of these min-max theorems that it's, it's very interesting, because we started off with, so you have a graph and you have towards these S and T, and suppose you wanted to show that there cannot be a flow bigger than a certain number. Then it suffices to get a cut of a certain size, and there can't be a flow more than that. Right? And what this theorem says essentially is that this is essentially the best way you can do things. So this is again related to duality, as we saw. So okay, so these are things we saw somewhat in the beginning of the course, and then there is this general question of can you always find good algorithms? So this is one of the big open problems. We don't know. Okay, so. And this is a P versus NP, but we said that there are many problems for which we believe that you cannot do this, and these were this whole class of NP hard problems. Okay. So we saw this notion of NP completeness. And and then the second part, so this is what, these are the topics you would find in most algorithms courses. So, and these are the basics in some sense. All of you should be pretty familiar with these kind of things. Then we saw some interesting notions which I think are, so these are quite crucial in modern algorithm design. Okay, so things like randomness. Okay, so randomness is something that people use in algorithm design all the time. So things like good hash functions and so on. Okay, so we saw how to analyze these things, and we saw these examples of balls and bins type processes and so forth. And the key things were how to think about the expected running time of these algorithms. Okay, so we saw things like quicksort, where it is actually much simpler than any other sorting algorithm. Okay, quicksort probably is not much simpler, but it's simpler to implement than some other algorithms. And the expected running time is still pretty good. Okay, in your homework you saw the min-cut example where the algorithm is actually really simple. And hashing. I think many of you are doing a project related to some randomized algorithm or the other. And then we moved on to this notion of linear programs. Okay, so these were, so we said that it's a very powerful way to capture even combinatorial problems. Okay, so as stated, a linear program is just, you have a bunch of linear constraints. Each constraint is like a hyperplane. It defines some region which we call a polytope, and you want to optimize a linear function over these. So, as stated, the domain is all of real numbers. You can restrict things to be 0, 1. Okay? You can restrict variables to be 0, 1, and that's what we call an integer linear program. And integer linear programs can actually capture NP-hard problems as well. And we said that sometimes you can just drop the integrality constraints, pretend that they don't exist, try to come up with a useful solution nonetheless. Okay, so this was what was the whole paradigm of relaxation. So I think in the makeup homework and in the practice final you'll see some very simple problems about these kind of things. We also saw this notion of duality, which is very powerful. So we started off with, you have a bunch of linear constraints, how do you show that they are infeasible? We said that the infeasibility itself could be written as a set of linear constraints. Okay, and that set of linear constraints is called the dual of the original set. And this is how we introduced duality. Okay, and last week we've been seeing things where the algorithm doesn't know the full data, can it still do okay kind of questions. Okay, so this is what we also saw just now. Alright, so just a quick show of hands. So among these topics, did people have favorites for the topics? Or was there something that you felt was, you'd like to have seen more, was not covered in enough detail, stuff like this? Any comments about the topics? Because this is the first time actually that I'm doing this course, so I have flexibility to change topics for next time too. So, before that, there are a couple of things that I chose not to do because there are actually courses that do this. Okay. So one is parallel or distributed algorithms. Okay. So these are things where you try to make use of the fact that you have lots of machines at your disposal. Okay. So this is often true in companies, big companies. And can you leverage parallelism? Okay. So there are some algorithms where you can believe that you can leverage parallelism. Okay. Suppose I tell you I want to do max flows in parallel. Okay. Now max flows involves computing augmenting paths every time, right? So that's an intrinsically iterative process. Okay, so you compute some flow, compute the residual, compute the augmenting path, and so on. Okay. So for these kind of problems, it's not clear that you can actually do these in parallel. Okay. So there's this question of what kind of problems can we solve in parallel. Okay, so this is something which it's a course of its own, so I didn't want to do too much. I didn't want to really get into that. Okay. And so there's a course by Hari. I don't know how frequently he offers it, but I think it's once in 2 years. Okay, so and that would be an interesting resource for that. Okay. So this is another course which I offer in the spring, which won't happen this spring, but it happens every alternate spring. And this is a course mainly on approximation. Okay, so this is something we've been seeing every once in a while in class. Okay, we see that the algorithm does at least half as well as the optimum and so on. Right? So how you formally study these kind of things, and there are many more techniques for coming up with algorithms like this. Okay? And there's this also notion of hardness of approximation. It says that for some problems you can't even approximately solve them. So or we don't expect to unless P equals NP. So so that's this whole notion of approximation. It arose once in a while in our course, but not explicitly. Okay. So these are two topics that I just decided not to do. Okay. Alright, so any comments on the topics we did and the pace at which we did them and so forth? Feel free to, you can also write in the course feedback, but it's just easier if you, since we have the topics. Yeah.
Can you focus more on like the NP hard, NP complete? I'm not sure if others have the difficulty, but
okay. Yeah, that's a good point. So okay. So you mean in terms of defining in terms of the definitions, or more in terms of more examples?
more examples.
Oh, more examples. Yeah, that's easier. Okay. Yeah.
I thought the flow homework was probably the funnest homework. Those were good problems, so
Oh, okay.
don't get rid of those.
That's yeah. I actually thought I did a bad job on those because I couldn't find many interesting problems. But I'm glad that you found them interesting. Yeah. Yeah.
I found the randomization stuff the most difficult to follow.
Yeah. So that is I think if this is the first time you're seeing these kind of things, I would imagine that in some sense it's one of these things that everybody finds difficult the first time. Okay, so you've just got to see it a lot of times. So, but you're right. So I should think about how to make it probably better. Okay, so yeah, I'll think about that. Okay. So do you have any suggestions about what specifically was difficult?
Maybe more examples that go through Markov's versus
Right. Yeah, actually, I felt this too. I tried to do some of this in the homeworks, but it's good to do examples in class. I agree, because I think we only saw this example of balls and bins. It's probably a little too restrictive. Yeah, that's a good thing. Yeah, other comments like this? Yeah, these are all very good. Yeah, that's a good suggestion. Yeah, I decided I decided to not spend too much time because I thought that you really learn these things only if you do it yourself. Some of these things. So that's but I could show examples. I think it makes sense. Yeah, other suggestions.
A little bit on other complexity classes.
Oh yes, that's again a very nice thing. Yeah. So I realized that we don't have any complexity course in the university, so it's something that we guys should think about. Yes, yeah. So this is there are actually a lot of very interesting things, and even when it came to randomization, I didn't talk about complexity per se. There's a whole very beautiful theory about how. In some sense, the basic question in randomization is randomization even necessary? Okay? And we don't know the answer to this question. Okay? And there's this beautiful complexity theory about how de-randomization is connected to other classical notions of complexity. Okay? So de-randomization is this notion where you have a randomized algorithm and you try to solve the same problem but without using randomness. So that's what's called de-randomization. And sometimes it is possible to de-randomize algorithms, but we don't know if all algorithms can be de-randomized, for example. Okay, so and there's a lot of nice complexity theory around it. Introduction to some of these classes is probably useful. Yeah. So what about linear programs? I somehow, I felt if I had spent more time, I could have done more justice to this. But did you have any concrete comments on this? Like, is the notion of linear programs and generally duality, was it clear to everyone? Okay, good. Okay. Yeah, because you can write a lot of things as linear programs, and I think we didn't see enough examples of those. And this paradigm of rounding, relaxation, and so on is something people use all the time. So it's nice to see some more examples.
You can list any prerequisites topic-wise, like say for randomized algorithms, a lot of math background and probability should be required.
Yes.
So even if we are got out of touch, so we can go to that before class.
Yeah, that's a good point.
It will be better. And it's not very intuitive to think about, just like flows or graphs. It's like more diagrammatically you can think of it, but these are not very intuitive, so.
Yes. Yeah.
That might
Not very pictogram. Yeah. It's not graphically intuitive. Makes sense. Yeah. So actually, there are some very. Did I ever put links to basic probability background on the course page? Or did I put them after the lecture or something? Maybe I did not. Okay, so there are some very basic, very good surveys on basic randomness kind of background, the kind of background that you're talking about, basic probability background, like computing expectations and so on, which probably many of you have seen once, but you don't do it on a daily basis, right? So, so probability background is always good. Yeah, and arguably, I think many of you expressed this, that the homework on randomness was the hardest. Was that generally the opinion?
I guess along with the probability background, there were certain
like identities from calculus and so forth that I just didn't remember not having dealt with that for many years. So
Right.
just more general mathematical background for those things would be helpful.
Right. Yeah, I agree. So I think it's better to just put up some links before I do the class, I guess, right? A couple of weeks before. Yeah, that should easily be done. Okay. Yeah, great. So if you have other suggestions, feel free to write to me. And I mean, I don't really mind if you have critiques as well. So yeah, just try to. As I said, I mean, this was the first iteration, so it's always useful to get feedback. Alright. So, okay, so did you have other questions, or do you have specific problems on the homework or anywhere that you might want me to just show you how to do it, or topics where it's helpful to revisit? So we could also break now, and people who have questions could just come by, and I can do one-on-one also. Okay, so yeah, so this is something. And next class, I thought it could just be a Q&A also, but we'll see. So, yeah, any specific questions? Yeah.
Can you say something about how we should prepare for the final?
Oh, no, I mean, so, I mean, it's basically you try to go through the lecture slides, make sure you understand some of the things, go through the homeworks and the solutions, and make sure you kind of know how to solve them. That's about, I don't really know, right? So these are things where if you understand it, it's should be fine. So, yeah. So just try to understand the basic notions of each of these topics, right? Of the topics that seen here. So like, how do you solve the recurrence, and how do you, basic things about graphs. Yeah.
Did you post example final questions?
I think so.
Yeah, here.
Just check the discussion. I think I did on Sunday.
And are all the solutions for the homeworks that we've turned in posted?
Except the makeup. Yeah. Yeah.
Could you release that before next Sunday?
Yeah, I could do that. So, but you are supposed to submit it on
Or
Sunday.
before this Sunday, I mean.
Aren't you supposed to submit it on Sunday?
Yeah.
Yeah.
Maybe on Monday, right? So, yeah, I keep forgetting when you're supposed to submit. I might as well have done it. Yeah.
So I remember being a little confused when we were talking about analyzing whether something's can be efficient in the size of the input. When we are looking at whether to count, for example, simple mathematical operations like addition, sometimes we have to account for that because I guess these sums involved can grow very large. I guess I didn't have a good handle on when to count that or when not.
Yeah, so there's actually, right, so that's a very useful thing to know. So let me try to create some.
Like sometimes it seems like addition could be treated as like a, a constant size operation, and other times, that's because the operands can be growing, I suppose.
Yeah, so in principle, you're always supposed to keep track of how many bits you're adding. Okay, so the general, the right answer to your question is, it's basically that. So suppose you have two n-bit numbers. Okay. So adding them, So these are binary numbers. Often you're supposed to think of what's the complexity of writing down the input in binary. Okay, so the input size, whenever we refer to it, you think of the amount of space needed to write down the input in binary. Okay, and why binary? It's an arbitrary choice. Okay, so if you have like base 10 is always just a constant factor different from binary. Okay, so it's within constants this is pretty good. And yeah, so this is how you usually think of the input size. And when you are doing things like addition, subtraction, so forth, you've got to keep this in mind. Okay? So there was actually one homework that where I mean intentionally kind of glossed over this. And I think the dynamic programming homework, you had to compute the probability of certain events. Okay? So basically what you had to do was you were multiplying probabilities. Okay? And these are the kind of situations in which this issue becomes very, very prominent. Okay, so suppose you have some initial probabilities. Okay, so you have some P1, P2 of certain events, and each one, let's say to write it down, you have k different bits. Okay, and you have up to Pn. So when you compute the probability of the joint event, the number of bits keeps increasing, right? It's like the answer could actually have k times n bits. Still a number between 0 and 1, but to know the answer exactly, you've got to have k times n bits. Okay, and this is often not quite feasible. This is probably something that you run into when you implement any kind of numeric algorithms. Okay, so you keep running into these accuracy issues. And there's no very good way of dealing with these sort of things. I mean, people have various arbitrary ways. Okay, but when we are analyzing complexity, you have to think about that in principle. Okay, so in principle, you must think about this. Actually, when you do slightly more complicated things like Gaussian elimination, right? So what's the problem there? So the problem there is you have a bunch of a linear system of equations. Okay, so you have just a1, 1x1, plus a1 n xn equals b1, and so on. Okay, so you have m equations like this, and you want to find a solution. Okay, and the usual way to do this is by Gaussian elimination. So for a long time, until about 20 years ago, nobody knew how to do this in a way that you guarantee time that is polynomial in the input size. They always said the number of operations you do, the number of arithmetic operations you do is polynomial, but the precision issues were never worked out. So in fact, if you do Gaussian elimination in some naive ways, you can actually show that the size of these intermediate numbers could blow up exponentially. Okay, so the number of bits could actually become exponential. Okay, so this is actually one case where it's particularly bad. Okay, so and it was not known how to do it for a long time. About 20 years ago, people figured out how to get rid of these kind of issues. Okay, so it is in general a tricky issue. Just to answer this question. But sometimes we can choose to ignore it. Like if we want to ignore it, we specifically say that we assume a model of computation where you can multiply things in constant time. But you've got to specifically make that assumption. So yeah, I'm not giving a concrete answer because people treat it differently. Okay, so that's, yeah.
When you say exponential number of bits, are you assuming that the data types used are integers, or are you assuming floating points in W.
No, I am actually assuming arbitrary precision arithmetic.
Okay.
Okay, so you can, there are classes that implement these things. Because floating point and so on, they implicitly round, which creates errors. Right? So that's not what I'm assuming. I'm assuming these arbitrary precision things where the precision keeps growing. Yeah. And there we don't quite know how to do these kind of problems. And when you round, are you sure you're not making any mistakes? So that also is not known. I mean, that is, it's even trickier to analyze. Alright, so that's a good point. But did I give a somewhat convincing answer? Yeah, it's just different ways of thinking. But in general, you are supposed to think about these. Yeah, actually one of these practice final problems is exactly on this. So where, like for knapsack or for subset sum type problems, if the number of, in terms of the number of bits, it's exponential. But as far as the number itself goes, it's polynomial. Right? So you can solve a problem in what looks like polynomial time, but in terms of the number of input bits, it's exponential. And that's what matters when you're talking about complexity. So, other thing to do here is review subset sum. Other questions?
Just looking at the practice final that's online, has the questions, is there any way to get a version that has like solutions as well, just to kind of see maybe how long you would expect an answer to be, or?
Oh, you mean how much detail?
Yes, yeah.
Oh, yeah, sure. So because they are, they're supposed to fit in that space. So the final, the practice thing also has an example of how the actual paper will look like. So you will have space to write the answers. So please bring some place where you can do rough work, because I don't want people working out stuff and then trying to fit in the answer in some very small space, which tends to happen. So please bring a notebook or something where you can do some calculations. Yeah, but this also I can do it.
Thank you.
Is the length going to be, I guess, is it going to be roughly the number of questions as practice, or?
The difficulty level will be the same, will be similar.
Right, the number of questions.
So, I think this adds up to something like 35 or 40. The final will add up to 50, so it will be a little bit longer. Maybe one question more. Other comments, questions? If not, just let's break now and anyone, if you have any questions, just come by. Okay, so I'll be here for a bit. Last week is always easy. Last week is always easy.